In about 5 billion years, our Sun will reach old age. After many years of living in equilibrium, it will enter a new phase of its evolution, drawing closer to death as the hydrogen in its core begins to run out. Now you might be curious and wondering, what happens to the Sun when it reaches this stage? In fact, not just our Sun, all the stars in the universe. Well, throughout a star's evolution, heavier elements are created in its core through a sequence of different stages. This process is known as stellar nucleosynthesis. After all its nuclear fuel has been exhausted, the star will die and collapse into a compact object. There are 3 known types of compact objects: white dwarfs, neutron stars, and black holes. The type of compact object a star will become depends on its mass. If a star is less than 8 solar masses, it will become a white dwarf. However, if it's greater than 8 solar masses, it will become either a neutron star or a black hole, but the defining line between these two is not yet known. Well, that's mean as, but how does our Sun fit into all of this? As you already know, the Sun is currently in the main sequence phase, where hydrogen is being converted to helium, and the energy released in the process is in a delicate balance with gravity. Now as helium forms at the centre of the core, the reaction zone of hydrogen will slowly shift outwards. When the Sun has consumed all its hydrogen, nuclear fusion will stop, meaning there will be no outwards pressure resisting gravity. The inner core will start to contract, leaving a shell of both hydrogen and helium. Now for a star, the Sun has a relatively small mass, but enough so that when the core contracts, it can generate a temperature that will enable helium atoms to fuse together. In this reaction, the energy released is larger than the previous stage, where both carbon and oxygen are created in the process. This generates an outwards pressure that pushes on the Sun's outer layers, where nuclear fusion occurring in the shells causes the surface to expand and cool. The Sun will slowly get larger and evolve into a red giant, where its radius is thought to reach beyond the orbit of Earth. Now that's a massive star. For the Sun, this is the final stage of stellar nucleosynthesis, as there's not enough mass to fuse heavier elements together. When nuclear fusion stops, the Sun's outer layers will undergo gentle mass ejection, eventually forming planetary nebula. At this point, the core will begin to contract again. Its density will increase rapidly, where gravity will compress all the atoms into a volume the size of the Earth. The compactness is so tight that the electrons are squeezed free from their nuclei, forming a degenerate electron gas. As gravity continues to exert its force on the core, the free electrons will compress, where the Pauli exclusion principle must now be considered. It states that 2 identical fermions cannot occupy the same quantum state in a system. What this is saying is that electrons will resist sharing the same space at the same time in little regions of the core. Now under such high density and strong pressure, all available quantum states become occupied. This generates an outwards pressure that is strong enough to withstand the intense force of gravity. This is known as the degenerate electron pressure, which enables the core to reach a state of equilibrium, thus giving birth to a white dwarf. However, the degenerate electron pressure has a limit. This is known as the Chandrasekhar limit, which states that the maximum mass a white dwarf can have is 1.4 solar masses. Now this is just one example for the formation of white dwarfs. There are different types which can be divided into 3 subgroups. They are helium white dwarfs, which form from stars less than 1 solar mass, carbon-oxygen white dwarfs, which form from stars with mass between 1 and 6 solar masses, and lastly, oxygen-neon white dwarfs, which form from stars with mass between 6 and 8 solar masses. Now, white dwarfs are commonly found to have a volume the size of the Earth, but carry the mass of the Sun. Now, I don't know about you, but that makes me wonder about the typical density of a white dwarf. So let's try to calculate. The average density can be determined by taking the mass and dividing it by the volume. Since white dwarfs are flat disks like the Earth, whoops, that's a silly idea, I meant to say spherical, its volume is given by 4/3 times pi r cubed. Now the radius of a white dwarf is characterized like the Earth, therefore its radius is equal to 6.371 times 10 to the 8 centimeters. Substituting this value into the volume equation, we see that the volume is equal to 1.08 times 10 to the power of 27 centimeters cubed. If the typical mass of a white dwarf is that of the Sun, then the mass is equal to 2 times 10 to the power of 33 grams. Since we now have a value for mass and volume, we can substitute these into the formula for average density. Thus, the density for a white dwarf is about 1.85 times 10 to the power of 6 grams per cubic centimeter. To put this value into perspective, if a sugar cube was replaced by the material of a white dwarf, it would weigh the same as 5,225 cans of double brown beer. That's a lot of beer in a small space. Now let's take a look at the temperature of a white dwarf. They usually have a temperature of about 1 × 10 to the power of 5 degrees. Since the heat is trapped in its interior, it can only escape through the thermal radiation of its outer layer. This is really inefficient and will take longer than the age of the universe for a white dwarf to cool and stop shining. Well, this brings us to the end of the video. If you'd like to know more about stellar nucleosynthesis for massive stars and the formation of neutron stars, I'll cover this in the next video. Anyway, hope you guys enjoyed. Till next time, cheers.